Hello and welcome to this A-level chemistry explanation video about the equilibrium constant Kp. You should already have encountered equilibria, Le Chatelier's principle and the equilibrium constant Kc. If you want a more detailed refresher of those, check out some of my earlier videos. This video will have some short recaps, but we'll spend most of the time looking at this new constant Kp. Chemical reactions can be considered to be either reversible or irreversible. In an irreversible reaction, the reactants turn into the products, the reaction maybe goes to completion, and this is the end of the situation. No further chemical reactions occur. In a reversible reaction, the reactants can turn into products, and under the right conditions, the products can turn back into the reactants. And this can happen continuously. Under the right set of conditions, we can reach what is called equilibrium. One of those conditions is that we need to have a closed system where no chemicals can get in or out, and we also need to satisfy a certain amount of optimum conditions such as temperature and pressure. A dynamic equilibrium recognizes that the forwards and the backwards reaction are both happening at equal rate, and as a result, the concentrations or the ratios of the reactants and the products is not changing. The equilibria that you will be encountering are going to be homogeneous equilibria, and that's where all of the reactants and products are in the same physical state or phase. And the two situations that you're going to encounter are where everything is a solution, so the state symbol would be AQ for aqueous, or where everything is a gas. There are a number of different types of equilibrium constant that you will encounter across A-level chemistry. Kc, Kp, Ka and Kw, and for some courses even more than this. What they have in common is that they are all a ratio worked out for a proportion of the products compared to the reactants. For Kc, for instance, we use the concentration values of the individual chemicals in an equilibrium mixture, and we look at their proportions of products to reactants. A big value means that the products predominate, or the equilibrium lies to the right-hand side. A small value means that the reactants predominate, and the equilibrium is largely to the left, and this will likely result in a low yield of chemicals. And that's one of the things that is powerful about the equilibrium constant. If the equilibrium constant is high, you can be confident for a high yield of your particular chemicals. The equilibrium constant Kp has a huge number of similarities with the equilibrium constant Kc, as you would probably expect. This extends to how we write the expression for the equilibrium constant and how we calculate its units, how we work out what its actual value is based on some moles data that we get in an equation, which we'll look more at later. And really the only difference comes from the fact that the P is to do with pressure, specifically partial pressure, whereas in the Kc expression, the C meant the concentration of the individual components. So the only real difference between these two terms is that Kp is concerned with the partial pressures of gases in an equilibrium mixture, whereas Kc is to do with concentrations. And you will encounter other equilibrium constant values as well, Ka and Kw. In a mixture of gases, each individual gas exerts its own pressure, and this is called the partial pressure. And this partial pressure, which is usually given the symbol lowercase p, is considered to be the pressure that this gas would exert if it occupied a container by itself. Now, the sum of the partial pressures for all of the gases in a mixture in a particular container is taken to be the total pressure. And the best example to illustrate this is if you consider a room filled with normal gas. We know that the two main gases in this room are nitrogen and oxygen, approximately 80% nitrogen and 20% oxygen. We also know from the ideal gas equation topic that all gases behave in the same sort of way, and that standard conditions have this room as having a total pressure of 100 kilopascals. Now, the concept of partial pressure dictates that if 80% of all the gas in the room is nitrogen, then the partial pressure of nitrogen is 80% of the total pressure. So, in this case, 80 kilopascals. And the oxygen would simply be 20 kilopascals. Together, these two partial pressures add up to the total pressure experienced in any particular room. And so as a general expression, you can say that the total pressure in any container, usually given a capital P, is equal to the sum of all the partial pressures of all the component gases in that mixture. And that's written like this, with a lowercase p given for the partial pressure of each thing. And we might typically write the identity of the gases in the way that I've done here. It's really important that you can construct an expression for Kp, and this might be a standalone question or the beginning of a calculation. The way that you do this is the same for all equilibrium expressions. We always begin by writing the equilibrium constant is equal to, and then we're going to have a fraction, and on the top of the fraction we're going to write the products, and on the bottom of the fraction we're going to write the reactants. And so C is the first of the products, so we need to put that in. We're using Kp, so we're using partial pressure values. So we need to use that lowercase p to indicate the partial pressure of chemical C. And then the other product is D, and so we need to write the partial pressure of D here. We're multiplying these two terms together, so really we should put a multiply symbol in this place. And then the reactants go on the underneath, so the partial pressure of A goes in and the partial pressure of B goes in. And this is the end of our Kp expression finished. It gets more complicated when you have a more complicated equation to work with. In this situation, you can see again, we've got the dynamic equilibrium, and we've got this time though, 2 moles of W reacting with 1 mole of X to make 3 moles of Y and 1 mole of Z. So we follow the same principles as before. We write Kp equals, and we're still going to have a fraction. This time when we put the products on the top, we need the partial pressure of Y cubed. Now, the best way to do this, to show that it is the term that is being cubed rather than that 3 maybe being the number of a particular atom present, is put a bracket around the partial pressure of Y and put the cube symbology out on the outside of those brackets. This is then going to be multiplied by the partial pressure of Z, and then we're going to divide this by the reactants, so the partial pressure of W squared this time, again with those brackets, multiplied by the partial pressure of X. So you only need those brackets when you're squaring or cubing or any other power for a particular chemical's partial pressure. If we take a look at this Haber process equation for a real-life example, we can see that we've got 3 moles of hydrogen gas reacting with 1 mole of nitrogen, then we're producing 2 moles of ammonia. So you can see that we don't need to have the same number of chemicals on either side of the equation. That's totally up for grabs, totally interchangeable. Constructing the Kp expression works in the exact way that you would expect. We write Kp equals, and then we need the partial pressure of ammonia on the top. That is the only product. We need to raise it to the power of 2 because we've got this coefficient 2 in front of the ammonia, so we need to have that power 2 in the Kp expression. We don't need to include the state symbol for ammonia. That's the same for any Kp expression, or in fact Kc. You don't need to include units inside the expression for an equilibrium constant. And then to finish this off, we'd have partial pressure of hydrogen cubed on the bottom, multiplied by the partial pressure of nitrogen. No power here because the coefficient is a 1. Calculating the units of Kp is really similar to calculating the units of Kc and quite similar to calculating the values of the rate constant. To start this process off, you need to begin by writing the Kp expression. You can see I've got 3 examples of equilibria here. I'll write the Kp expressions for each of them. And then we need to substitute in, instead of any values, the units for each of the terms. So you can see in this first example, because I've got 3 product terms on the top of the expression, I need partial pressure 3 times on the top. and we've got two reactant partial pressures, so I need partial pressure twice on the bottom. And then we need to cancel out commonality on the top and the bottom. So the first partial pressures cancel out, and so do the second. And so what we're left with is just one partial pressure on the top. And so the units of kp are likely to be pascals, or possibly kilopascals, or possibly atmospheres. That's the slightly frustrating thing. You need to look at the data that you've been given in the question and look at the units in particular for these data. And that could be, as I say, pascals, kilopascals, or atmospheres. So you need to stay on the ball and substitute in accordingly. And as I say, in this particular example, it would just be kilopascals, for instance. If we take a look at the second one, you can see that we've got partial pressure twice on the top and 4 times on the bottom. And so once we cancel out 2 of those partial pressures from the top and the bottom, you can see that all we've got on the top is a 1, and we've got partial pressure squared on the bottom. As with anything that is a 2-line fraction for units, we need to get that all onto 1 line, and so we bring that partial pressure squared on the bottom up to the top, and so we've got partial pressure to the power of -2. Again, we're faced with the situation of what data were we given in the question. If it was kilopascals, the units would simply be kilopascals to the -2. Or if it was atmospheres, it would be atmospheres to the -2. And then in my final example, I've chosen a situation where we've got an equal number of moles of gas on both sides of the expression. And so as a result of that, we've got 2 partial pressure terms on the top and 2 on the bottom. And so when we do our cancelling out, they cancel out perfectly. And so we've got a situation here where in fact there are no units for the equilibrium constant of Kp, and that's something to remember because it will speed you along in a question that if you've got the same moles of gas on either side of the expression, there are no units for Kp. When you're calculating a value for Kp, you of course need to have the Kp expression. So if we consider an example here where we've got PCl5 turning into PCl3 and chlorine, and the partial pressures are 288 kilopascals for PCl5, 463 for PCl3, and 163 for Cl2. We can actually calculate a value for Kp very easily here by substituting in those values that I've just said for each of the individual chemicals. Having done that, we get a value of 262 for our Kp. Now we can work out the units in the exact same way that we've looked at previously. We've got 2 partial pressure terms on the top and 1 partial pressure term on the bottom. So that means that there's going to be 1 cancelling from each of those positions. And so the units are going to be kilopascals. So our final answer, 262 kilopascals. You might be asked to calculate a value for a partial pressure of 1 chemical or a number of chemicals. This could be as a standalone question or as part of a Kp calculation. To do this, it's the same whichever the particular ultimate goal is. Now, we need to recognise and remember that the partial pressures of all of the chemicals at equilibrium add together to make the total pressure of the closed system. And so if the total pressure is 40 atmospheres, then that means that the sum of all the partial pressures of all the chemicals adds up to 40 atmospheres. And so you might get a breakdown like this, where you've got a 10, a 10, and a 20 for the 3 chemicals at equilibrium. To go in the other direction to work out what those partial pressures are, you need to know what the proportions of those chemicals are. And to do this, we use something called the mole fraction. Now, the mole fraction is very obvious. If you've got a certain number of chemicals, each with a different number of moles, the mole fraction is the moles of that chemical that you've got divided by the total moles of all of the chemicals at equilibrium. And so if you've got one chemical which you've got 2 moles of, another chemical you've got 3 moles of, and another chemical that you've got 5 moles of, the total moles of chemical at equilibrium is, of course, the sum of those 3 numbers, which is 10. And so the mole fraction of the first chemical is 2 divided by 10, 0.2. The next chemical is 0.3 and the final chemical is 0.5. So now we know that the mole fractions of these chemicals are 0.2, 0.3 and 0.5. You should note that these mole fractions all add up to 1. If they don't, you've not done it correctly. The final step now is to calculate the partial pressures of these individual chemicals. And so if you have got a total pressure, say, of 50 kilopascals, you know that each of these partial pressures is going to add up to 50 in total. So the first chemical that had a mole fraction of 0.2 is going to be contributing 0.2 of that 50. So that's, in other words, a fifth of that 50. Now, the calculation that you need to do is mole fraction multiplied by total pressure is equal to the partial pressure. And so 0.2 multiplied by 50 gives us 10 kilopascals for the first chemical. The next chemical is 0.3 of that 50 kilopascals. So we do 0.3 multiplied by 50, which is 15 kilopascals. And the final chemical is 0.5 of that 50, and so that is 25 kilopascals. And it's worth doing a quick bit of mental arithmetic. 10 plus 15 plus 25 does indeed make 50, so we've calculated this correctly, and we've got our partial pressures. This is the same process, whatever the equilibrium moles are, however many chemicals you've got, whatever units the total pressure is in, you follow this process. Le Chatelier's principle states that a chemical system at equilibrium will shift to oppose any externally applied change that we might choose to do. And so this will typically involve a change in pressure or a change in temperature or a change in concentration of any of the reactants or products. And so we can use Le Chatelier's principle to manipulate an equilibrium to maximize the yield of a chemical that we're trying to make. Now, in the context of an A-level chemistry exam question, you're likely to be asked to state how Le Chatelier's principle might affect one of a number of things. This might be the position of equilibrium, in which case that is how you would expect. It might be that you're asked to state how it might affect the yield, and again, that will follow the effect that you would expect. Or you might be asked to state how this would affect the value for Kp. And this is identical to any equilibrium constant value. And this is really important to get locked in your brain, is that the only thing that will affect the value of any equilibrium constant is temperature. Either an increase or a decrease, both will affect the value of the equilibrium constant, but nothing else will. Not a catalyst, not concentration, and not pressure. Those will not affect the value for Kp. They will affect the position of equilibrium and the yield of a particular chemical. And so if we look at the example that we keep using, the Haber process, you can see that you've got 4 chemicals on the left-hand side and 2 chemicals on the right-hand side. So if you raise the pressure, the equilibrium is going to shift to try and decrease that pressure and counteract that change. That means it's going to shift to the right-hand side, and so that means that we will get more ammonia. And so that's likely to be something that we would choose to do, to raise that pressure. Obviously, this will have high costs in terms of the energy required to run the experiment, and also high costs in terms of buying the equipment to withstand that high pressure. But it will get us a better yield, which is what we want. The reason that it won't affect the value for Kp, even though it might suggest that it will, is as follows. So firstly, why might you expect it to affect the value of Kp? Well, the equilibrium has shifted to the right-hand side, so surely Kp will go up. That's the first clause. Now, if we look at the Kp expression, though, that we've constructed before, the way that we raise the pressure is by increasing the total pressure of the system. Now, because we've got more terms on the bottom of this expression, the partial pressures are going to be increased across the board because the total pressure has gone up. But this will have a greater effect on the bottom because there are 4 partial pressure terms on the bottom that are going to get larger and only 2 partial pressure terms on the top that are going to get larger. As a result of that, you would expect the Kp value to go down. So we've got 2 conflicting pieces of information. The shift in equilibrium states that Kp should go up. The Kp expression itself states that Kp should go down. Those changes will be exactly equal and opposite and cancel each other out, and so Kp will not change. If we explore the only situation where Kp does change, if we stick with the Haber process, this is an exothermic process. So if we raise the temperature, the equilibrium will shift to the left-hand side. That will not affect the Kp expression directly. It is only affecting the equilibrium position, and so because we've shifted it more towards the reactants, that means that Kp is going to go down because we're going to have fewer products and therefore a lower partial pressure of the ammonia, and we're going to have more reactants and higher pressures of the hydrogen and the nitrogen. This would obviously be the opposite if we had any endothermic process. Raising the temperature would shift equilibrium to the right-hand side, more products, higher partial pressure of the products, therefore larger Kp as a result. Calculations of Kp can be made more complicated when you have to work out the partial pressures first. To do this, you're likely to be given a starting number of moles for the chemicals on either side of the equation. And so here, let's say that we've got 10 moles of nitrogen and 28 moles of hydrogen at the beginning. Unless you're told anything different, you should assume that the moles of the chemicals on the opposite side of the equilibrium is 0 at the start. So this is the initial moles of the chemicals. And then you'll be told one fact about the equilibrium moles of the chemicals. So in this instance, I'm going to declare that there are 6 moles of nitrogen present at equilibrium. So then what we need to do is work out what the change in the moles of nitrogen has been. So you can see down the side I've got the abbreviation ICE, and that's quite a helpful memory aid. So the change is from 10 to 6, so that's obviously -4. You'd expect the left-hand side to go down because those are the reactants. So the nitrogen has gone down by 4. But if you take a look at the coefficients, the nitrogen has got a 1 for its coefficient, and the hydrogen has got a 3. And so that means that the hydrogen will go down by 3 times more than the nitrogen does. So nitrogen went down by 4, hydrogen will go down by 12. So the equilibrium moles of hydrogen is going to be 28 minus 12, which is 16. The ammonia has got the coefficient of a 2. It's on the opposite side of the equation from nitrogen, which means its amount will go up. Nitrogen went down by 4. Ammonia is going to go up by 2 multiplied by 4, which is, of course, 8. And so the equilibrium moles of ammonia is 8. This is standard for any equilibrium constant calculation, but specific for Kp now, we need to work out the mole fraction of each of our equilibrium chemicals. And to do this, it is the moles at equilibrium of each chemical divided by the total moles. So we need to work out the total moles. 6 add 16 add 8, which is 30. And so the mole fraction is 6 over 30, which is 0.2, 16 over 30 for the hydrogen, which is 0.53, and 8 over 30 for ammonia, which is 0.27. We can always double check this because the sum of these mole fractions needs to add up to 1, and it does in this instance. And because we're using Kp, we need to ultimately be using an expression with partial pressures in. So to work out the partial pressures, we need to take those mole fractions and multiply them by the total pressure, which you must be given in the question. You're not expected to remember this. If you're not given a total pressure, that's because there are equal number of moles on both sides of the equation, and so you don't actually need it, and you can just use mole fraction. And so for here, we do need a total pressure, so let's say that the total pressure is 4 atmospheres. That means the partial pressure of nitrogen is 0.2 multiplied by 4, so 0.8. Hydrogen is 0.53 multiplied by 4, so 2.12, and ammonia is 0.27 multiplied by 4, so 1.08 atmospheres. Now we've got our partial pressures, we need to work out the Kp expression. So that will have the products on the top, remember. So the partial pressure of ammonia squared divided by the partial pressure of hydrogen cubed, because of that 3 in the equation, multiplied by the partial pressure of nitrogen. So now we substitute in those partial pressure values that we've calculated. We've got 1.08 squared divided by 2.12 cubed multiplied by 0.8. That will then calculate down to this, which ultimately gives us a final answer of 0.153. In terms of the units, just a quick refresher, we've got 2 pressure terms on the top, 4 pressure terms on the bottom, and so that will then cancel down to 1 divided by pressure squared, and so that means when we bring the pressure terms up to the top, we've got pressure to the power of -2, which is atmospheres to the -2. So our value of Kp is 0.153 atmospheres to the -2. There are a few ways that you could be asked to carry out Kp-related calculations without being asked to solve the expression to find a value for Kp. Firstly, you might be asked to calculate the mole fraction of a set of chemicals using mass values. This will use the equation mass is equal to mR multiplied by moles. We'd rearrange that to find mass divided by mR is equal to moles. Then we would have the moles of all of the chemicals at equilibrium, and then we could solve for the mole fraction by adding up to get that total, and each equilibrium moles divided by the total would get us the mole fraction. Alternatively, we might be asked to use a Kp expression, but you might be given a value of Kp, and you might be asked to solve that equation for a particular partial pressure. And so to do that, you would substitute in all of the numbers that we do know, so that would be the value for Kp and the partial pressures of all of the other chemicals, and then we'd rearrange that and solve for a partial pressure. Alternatively, but very similar, we might be asked to do almost the same thing, but to use a Kp expression to find a mole fraction. In this instance, we'd have to be given the value of Kp, we'd have to be given the partial pressure of most of the other chemicals, and we'd have to be given the total pressure. Because here we'd do the same thing as number 2, where we would rearrange the values that we've substituted in. That would allow us to calculate a partial pressure for this unknown chemical. And then since we know that partial pressure is mole fraction multiplied by total pressure, we would know that mole fraction is equal to this partial pressure that we've calculated divided by the total pressure. And then the final thing that we might be asked to do is to use a Kp expression to find an unknown total pressure. To look at an example of this, if we take the PCl5 equilibrium that I'm showing here, and let's assume that we've got equilibrium moles that we know, and so the PCl5 equilibrium moles is 6, PCl3 is 10, and Cl2 is 4. And let's say that we know that the equilibrium constants value is 80 atmospheres. We would need to know at the very least these data in order to calculate the total pressure. So we can work out what the Kp expression is going to be. It's the partial pressure of PCl3 multiplied by the partial pressure of Cl2 divided by the partial pressure of PCl5. And that's why the units are atmospheres. We can work out what the mole fraction is by working out the total moles, which is 20. And so PCl5 is 6 divided by 20, PCl3 is 10 divided by 20, and Cl2 is 4 divided by 20. Since partial pressure is mole fraction multiplied by total pressure, we can substitute this in to our Kp expression, and let's just use the capital letter P for this unknown total pressure. And so we've got 80 is equal to 0.5 P multiplied by 0.2 P divided by 0.3 P. And now the temptation is to use a quadratic, because what you'd be left with on the top is a p squared term and a p term on the bottom. It is much easier than that, because what you've really got is p squared divided by p, and this will obviously cancel out to just one capital P on the top. And so when we do that, we end up with 0.333p being equal to 80. And then when you do 80 divided by 0.333, you find that the total pressure is 240 atmospheres. And this would be our final answer. I'm going to finish by giving you some hints and tips about KP related questions. First of all, an all-important reminder, remember that KP's value is only affected by temperature. The next hint comes from if you've got what's called equimolar equilibria. So you've got the same number of moles on both sides of the expression. That means that the equilibrium expression will not have any units, so you don't need to go through any process of calculating that. You can just look at the coefficients on both sides of the expression. And so not only that though, if you've got the same number of terms on both sides, if there won't be any units, you don't actually need to go through the motions of multiplying mole fraction by total pressure. Because what you're going to do is multiply mole fraction by total pressure, say twice on the top, and then divide that by mole fraction multiplied by total pressure twice on the bottom. And so that means you've got two total pressures on the top and two total pressure terms on the bottom, and those will all cancel out. So in fact, for this particular situation, you can in fact calculate Kp by simply using mole fraction values for all of the chemicals at equilibrium. And in fact, since mole fractions are calculated by taking equilibrium moles and dividing each of them by the same total number of moles, you can in fact use simply equilibrium moles instead of mole fraction values. The final hint and tip I want to give you is if it feels like you need to use a quadratic to solve an equation and find a value for something, then you've done it wrong, or there's an easier way, because for A-level chemistry, you're not going to be required to use quadratic expressions. The most common solution in this situation is going to be to square root both sides of this expression. You can encounter this if you've been given a value for Kp and a starting partial pressure for a particular chemical at equilibrium, but you haven't been given any of the equilibrium moles. So for instance, if you've got hydrogen fluoride turning into hydrogen and fluorine, and you know you've got 80 kilopascals of hydrogen fluoride at the beginning, what you can do is you can say, make the moles of hydrogen produced at equilibrium be X. And so the moles of fluorine produced at equilibrium will also be X. And then the moles of hydrogen fluoride that you start with is going to be 80 minus 2x, because since we've got the coefficients of 2, 1, 1, that means the hydrogen fluoride will be used up at twice the rate that hydrogen and fluorine will be produced. And so then we will get an equilibrium expression that will look like this. And you can see that we don't know quite a lot of the things to do with these equilibrium values. Let's say the equilibrium constant is 0.04, then we can see that we've got 0.04 is equal to x squared divided by 80 minus 2x squared. And so that makes us feel like we're going to need a quadratic to solve this. But if we take the square root of both sides of the expression, you can see that we've now got a much easier, not easy, but a much easier situation to solve. You've got 0.2 is equal to x divided by 80 minus 2x. To solve this for x, we need to then quickly rearrange this equation, and we get 0.2 times by 80 minus 2x is equal to x. And this then simplifies down to 16 minus 0.4x is equal to x. And then 16 is 1.4x, and so x is 16 divided by 1.4, which is 11.42. And this is the partial pressure of hydrogen and fluorine at equilibrium. And so we can adjust our calculations from higher up the page now. And then that means that the partial pressure for hydrogen fluoride at equilibrium is 80 minus 11.42 multiplied by 2, which is 57.2. Okay, that's the end of this video. I hope it was useful. I'll see you again soon.